In today's tutorial we will discuss the bromination of phenanthrene in detail. This bromination is especially interesting because the mechanism combines both aspects of the bromination of an olefin and aspects of the electrophilic substitution of an aromatic system. The reactive part of the phenanthrene is within the central, still slightly aromatic ring. It is this double bond between the positions 9 and 10. We start with the situation we have bromine and will add it to phenanthrene, normally a solution of phenanthrene in some kind of neutral, non-participating solvent. Let's have a look at the energy reaction pathway diagram. We choose an energy level for A. Let's say we simply start here. First intermediate will be a so-called pi complex, where we have a loose association of the bromine molecule with the pi system, preferentially with one bromine in front sitting on top of this pi bond. Does the energy level compared to A go up or down? Well, it certainly will depend on the solvent that we will use. For this diagram, I decided this whole interaction reminds me of some kind of solvation, and this is energetically favored. So from A to B, I decided to go with B slightly beyond the energy level of A. But certainly in the next step, we will go upwards to a reactive intermediate we are well familiar with from the bromination of, for instance, cyclohexene. A bromonium cation is formed, rather strained system, and well, this is certainly a reactive intermediate way up on the energy level. Next step, the bromide could start or undertake a nucleophilic substitution, some kind of SN2 process, and will or could directly lead to this addition product. That is the mechanism we are used to from the addition of bromine to cyclohexane. On the other hand, it is also possible that the CBr bond is broken and another reactive intermediate will be formed, a benzoic cation, where the cationic charge is mesomerically stabilized by this phenyl, this benzene ring. Actually, it is also possible that from the pi complex directly this benzyl cation is formed. If we compare the energy level of the bromonium cation with This benzyl cation, this one should be lower in energy, energetically favored. So there is the possibility that C goes to D. And now from D, it is also possible that the bromide does not react as simple nucleophile going to the addition product, but as a base deprotonating here, and then the system, the phenanthrene system, re-aromatized, and we get 2F. So if we compare the energy level of the dibromo dihydrophenanthrene and the 9-bromophenanthrene plus HBr, then this is certainly the thermodynamically favored product. So its energy level is beyond that of E, the addition product. However, this bond formation is certainly a bit faster compared to that deprotonation. That means that this is kinetically favored. So, if we perform the reaction on rather low temperature, we will be able to at least spectroscopically detect product E, but at somewhat higher temperature, and that means 0 degree or even better at room temperature, certainly wait a little bit, and then the thermodynamically favored product will be formed in rather high yield. Thank you for listening. See you next time again.